Okay, so let's look at another function and find the critical numbers for this function. So the procedure is find the derivative. So we're going to have 4/3 times 3x squared plus 10 times 2x minus 24. And we're going to set that equal to 0. So it's going to look like 4x squared plus 20x minus 24 equals 0. So hopefully you're seeing a GCF of 4 there. So factor out the GCF of 4. And you can actually divide both sides by the 4 to see that the 4 has nothing to do with when is this function 0. The 4 has no effect on when is this 0. So then we're going to want to factor. And we're going to have x plus 6 and x minus 1. And then we're going to use the zero product property that says these two things multiply together to 0. One or the other of them has to be 0. So that's going to allow us to find our critical numbers of -6 and 1. And that's all that's being asked. So don't do more than you're asked, but do all that you're asked. Determine the critical numbers. We're done. We have found the critical numbers. So then we can use those critical numbers, just as we did in the previous problem, to find the intervals where the function is increasing and decreasing. And then there's another important bit of information we can also get. So we're going to take a little detour and learn about that, and then come back and finish that example. So once we know where a function is increasing and decreasing, we can figure out whether it has any local extrema. So let's talk about these points on this graph. And first of all, scribble out the part with the arrows, and let's assume that it's just this little piece of the graph from the red dot to the red dot. So then we would say at x1, this function f has a local max. It's the highest point in its neighborhood. And we could also say at x3, f has a local max. So see why we say extrema, because there can be more than one local maximum. It's in its neighborhood, it's the highest point. But then we have another term that we use, and we would say at x1, f has an absolute max. So that's the very highest point you ever get to on this function you're looking at. So local max is in your neighborhood. Absolute max is I'm looking everywhere, and that's the very highest point. So then we can also say the opposites, where at x2, f has a local min. And at x4, f has a local min. And then at x4, we could also say f has an absolute min. Okay, so we're going to be able to find those points by looking at what happens with the derivative. So if to the left of the point the derivative is positive, so here we have the derivative is positive, the slope of the tangent line is positive. And then to the right of that point, we have f prime is negative. Then we're going to know that point where the derivative is 0 has to be a maximum. So right at this highest point, the tangent line will be horizontal with a slope of 0. So that's why we're finding those points where the derivative is 0. They're going to be important points. They might be maxima or minima. And then point x2, notice that on the left the derivative is negative. On the right, the derivative is positive, and at that point, the derivative is 0. So if your derivative goes from negative to 0 to positive, then you know this point has to be a local min. Okay, so we're going to use that information. Now I want to take a moment here to talk about when you find where the derivative is 0. So this is a one-directional true statement that if you're at an extreme value, the derivative will be 0. So let me write it that direction. If you are at an extreme value, f prime of x will be 0. The derivative will be 0. But finding someplace where the derivative is 0 only might give you an extreme value. It doesn't guarantee you one. It doesn't necessarily say you will find one. So this is really important that you understand the logic here. So here's a parallel example. If it's raining, there are clouds. Okay, that's a true statement. If it's raining, there are clouds. But the opposite statement is not necessarily true. If there's clouds, it might be raining, but it isn't necessarily. So you can't just find where the derivative is 0 and say, oh, I found a max. You need more information. So this is kind of a famous, what's called a counterexample. So let's look at the graph of x cubed. And its derivative will be 3x squared. So if we set that equal to 0, that's going to happen when x is 0. So when x is 0, the derivative is 0. But look at the graph. Clearly, we don't have a max or a min. This function is always increasing. So this is the perfect example of I found a place where the derivative is 0 and it's not a max or a min. So when you find where the derivative is 0, it's possibly a max or a min. But you don't know yet until you get more information. Okay, so we're going to come back to this same example we were working on above. So it's the same example. So we're going to bring our critical numbers down here. And let me just write the derivative again so we have it handy. So our derivative was 4x squared plus 20x minus 24. And our critical numbers were -6 and 1. And it's super important that you get the derivative correct, you get your factoring correct, and you solve correctly. If you have errors in any of those, the rest of the problem won't work out. So this row just below the number line is x values. It's our critical numbers. And so we know that at the x value of -6, f prime is 0. And at the x value of 1, f prime is 0. So we can fill that in on our chart. And then leave a little bit more room underneath here. Maybe leave 2 rows. And then let's do our chart with the interval and the test point. And then we're checking the sign of f prime to see if it's positive or negative. So our first interval is from -infinity to -6. So I'm going to use -10. And I want to calculate f prime of -10 and see if it's positive or negative. So I'm going to have 4 times negative 10 squared plus 20 times negative 10 minus 24. So you're welcome to just put this in your calculator, but I find it faster to do mental math, and that's why I pick the 10s and the 1s. So negative 10 times negative 10 would be 100 times 4, 400, minus 200 minus 24, so that's going to be positive. So everywhere on the interval from negative infinity to negative 6, the derivative is positive. Okay, so then we're going to look at the interval from negative 6 to 1, and yay, 0 is available. Love it when 0 is available. It just makes the arithmetic so easy, because f prime of 0, all the terms that have x's in them will go to 0, and you just get negative 24. So on the interval between negative 6 and 1, the derivative is negative. And then from 1 to infinity, I'm going to pick 10 and calculate f prime of 10. That's going to be 4 times 10 squared plus 20 times 10 minus 24. Again, I can see that that's positive, but you're welcome to compute it if you like. And so I'm going to say everywhere on the interval from 1 to infinity, the derivative is positive. So now let's see what we can say about the function. So if the derivative is positive, the function is increasing. And here from 1 to infinity, the derivative is positive, so the function is increasing. Then from negative 6 to 1, the derivative is negative, so the function is decreasing. So let's think about what's happening right at x is negative 6. So the function, as you go from left to right, is increasing, and then I get to a spot where the derivative is 0, and then I'm decreasing. This has to be a local max. And then when x is 1, to the left the function is decreasing. Then I get to a spot where the derivative is 0, and then it's increasing. This has to be a local min. Okay, so this process we just did is called the first derivative test, where you're using the positive or negative first derivative to draw conclusions about the function and find local extreme values. Okay, so let's look at this graph where you said critical numbers at negative 6 and 1. So here's this graph, negative 6, each of the x boxes is 2. So see if you can find where x is negative 6. And see, sure enough, we have a local max there. And when x is 1, we have a local min. So I'd really encourage you to go to Desmos and draw the graphs. It doesn't take that long, and then you get some verification of your math work and can kind of make sense of it visually. Okay, so let's look at another example. And so far, these have all been polynomials, just to get you started. So there are patterns to the derivative in polynomials that don't necessarily hold as soon as you get different kinds of functions. So don't assume that, for instance, the pattern went positive, negative, positive. That's just because this is a simple polynomial. That's not a pattern that you can count on. Okay, so let's find this first derivative of this function, and we're going to have 6x squared minus 6x minus 72. And we're going to set that equal to 0. And I'm going to start here and make an additional movie so that it won't be so long.